have domain symmetry, asymptote. These are the kind of things, the procedure. So the first four part, this part right here, this is what I call the non-calculus, the pre-calculus part. So when it comes to what the curve sketching, we have the pre-calculus part, and then we have the calculus part. Calculus part, number 5 and 6. And then based on all that, then now you get the charting and the curve sketching. Okay. And by the way, when you study, try to study. When you study with a file with no solutions first. Again, class, let me tell you, when you study for these topics here, first study with the file which has no solution. Don't just read the solution. If you open up the solution file, there's no mystery, and you will never get it. You will not study anything. So please study the file with no solutions first. And then once you spend about 10 minutes on each problem, or less, then I want to look at the solution and check against it. Okay, is that clear? Solution graph does not include everything here, but on this slide, section 3.5, I've given you many more examples. So, many more examples here. So, okay, so save, and then many more problems here. So I've written down all the first and second derivatives for you. Okay, these are all of this. Okay, so again, example 3, I've done all the work towards the second derivative. In example 4, so make sure that you use this as a practice to check your solution, but don't just open up the file. If you do that, you'll be wasting time. Okay, so you're not going to study anything. So please study with a file with no solution first. So this is section 3.35 solution. There's the file 3.5. So study with 0735. Don't look at the solution. And then when you want to check it, then you can look at it, okay? All right, and of course you can also use the graphing calculator to check your work. So now what I'd like to do is, let me now do section 3.7. Optimization. So the remaining hour, time for the session, I'll be spending on optimization. And yes, tomorrow's test will include optimization. Okay, so let's look at it. By the way, this is section 3.7. There's a file called section 0737 solution. If you open up that file, then all the solutions are basically out there. Okay, I've done all the groundwork. Let me see. If I open up here, let me see what does it show. Let me just show you how it's done. Okay, how come this file doesn't open? Let me see. Start opening here. Oh, there we go. Options in there. I'm all in the graphing chart. Yeah, there we go. You have to do a graphing chart here. Yeah, the graphing chart I didn't do, okay? So before we get there, let's look at this. So let's look at this here. Okay, so let's look at section 3.7. Okay, example 1. Find the minimum perimeter of a rectangle whose area is 16 inches square. So what is this? So it says here, example 1, find the minimum perimeter. And so now the title is optimization. The title of the section is optimization. What is optimization? Optimization means what? Optimization is what? Is finding what? This is what? Finding what? Maximum and or minimum.
Professor, is this the section do we use Newton's method in this section?
Oh, Newton's method, I'm skipping it, by the way.
Okay.
I think Newton's method is section 3.8. So which I'm going to skip. If because I'm kind of running out of time, and also the Newton's method is not a prerequisite to any of the later sections. Okay, so for those of you who will be taking what is it, numerical math later on, you might have to study the Newton's method on your own. The Newton's method is actually it's not a hard section, okay, relative to the other sections, that is, and it's simply a formula. Again, for those of you who are programmers, you might want to study Newton's method because it involves the iteration. Okay, so but anyway, the notes there, you're free to study and ask me questions. But due to time, I am skipping Newton's method. Again, Newton's method is, I think, it's section 3.8. Okay? 3.8. And I did not write any solution in that section because my plan was not to cover that section. Okay, but you can study, look at the questions, and you can actually there's not much in there. So if you read it on your own, it's a good section for you to study on your own. Okay. Okay. So now let's come back here. Section 3.7, optimization. Example 1. Find minimum perimeter of a function, minimum perimeter of a rectangle whose area is 16 squared. So it says you're finding the minimum perimeter. So as now you can see that we're trying to find the minimum perimeter. So this is an optimization problem. Okay, so optimization problem. How do we set up? So first of all, let's try to draw a diagram which will help us. So the diagram will help us here. So let's try to do that. So what I'm going to do is let's see. It says here find the minimum perimeter. So we have to minimize the perimeter. So the perimeter, this will be our objective function. That's the function which we need, and that's the function we will need to minimize. And then it says this problem is about rectangle. So what we want to do is let's let me now draw a rectangle. So let's draw a rectangle right here. Oops. Too thick. Let's do this. Okay. And so if you have a rectangle here, then, but the rectangle is up the area. So an area of perimeter looks like we need the two sides. So no question here. Why don't we just call them X and Y? Why do you want to call them X and Y? Because they talk about the area and they talk about the perimeter. And the perimeter and the area, they have to be expressed in terms of these two sides here. So there's not much choice here. For rectangle, basically, these are the two variables we have. So now, here's setup. The important part is setup. This is the part which is very important. And setup is, this is the critical part. So first, we start with the objective function. What is the function which we need to minimize or maximize? What is the function? Is that area? Or is that perimeter? What is it? Now, in this case, it says find the minimum perimeter. So if you see the word minimum or maximum, if you see the minimum or maximum, then what's the function which comes immediately after minimum maximum? That right there is what we call the objective function. So in this case, set up P. Set up P is the perimeter. So what is the perimeter in this case? The perimeter is equal to what? Perimeter is equal to X times what? And P is equal to X. P is equal to P is equal to XY. Sorry, not XY. It's 2 times X plus Y. Note that X must be bigger than 0, and Y must be bigger than 0. And note that to the two independent variables. Two independent variables. The way we calculate the number of variables is not the same as related rates. Okay? So for optimization, you look at the number of variables. P is just a name. We can create any name, but P for perimeter, and then we have two independent variables. That means if you have two independent variables, then I just want to let you know that we need what? We need one constraint. Need one constraint. Condition. We call them condition or constraint. So we have two independent variables, x and y. Any relation between x and y? Yes, we do. X and y, we have a condition. What is the condition? X times y must equal what, 16. And then is that the only condition we need? Is that the only condition we have here? Yes, that's it. And then now, lastly, we want to write the question. Find the minimum parameter. So that will be the question. And so this is now the complete setup. The complete setup is this guy right here. And if you give me the setup, correctly with no mistakes in one place like this, and put in a box or put in a parenthesis like this, then this is the complete setup. You'll be receiving at least half of the credit, half of the problem, half of the value of the value for the problem. If this problem is worth 10 points, the setup only, the complete setup, complete correct setup will get you at least half of the credit. If there's 10 points, you will get at least 5 points. For rectangle problems, you will get 5 points because rectangle is the easiest kind of word problem. That's why. So I'm not going to give you any more than 50%. So 5 points out of a 10-point problem. And by the way, this p is equal to 2 times x plus y. This is the function. This is the function right here. The p is the function in this case. P is the function. Function to be what? Maximize, max or minimize. The function to be minimized or maximized. This p is called the objective function. This p is called the objective function. Objective function. Function to be what? To be maximized or minimized. Minimized. There we go. The function which you want to minimize or maximize, we call that objective function. Our calculus textbook does not use this term, but this is a term which shows up in any business calculus. I borrowed this from business calculus, okay? In business calculus, or in general, in business, they actually call this objective function. Because in business, they always want to maximize and this, maximize that, or minimize that. And so they actually have a name. And it's, I don't know why, but a regular calculus textbook, they don't use this term, okay? So I think it is a term which one to use, because if you look at example, section 3.7, many of these are actually, they are business-related questions. Well, right now, not the easy ones. Well, actually, it is. We have area is 16. Let's say you want to store something, and then you want to surround maybe a fence, and then you want the area to be 16. What is the minimum perimeter, minimum fencing you need? So it is actually a business question. Again, example 1 is a business question. Let's say it's like if you want to make a can, and then you want to see how much, well, can is a three-dimensional problem. You can create one, but anyway, example 1, it could be thought of as a business question. Okay? It's like if you have a farm, and you need so much area, and then you want to see how much fence you need. Okay, so it is a business question. So business, they use this term, objective function. So in this case, P is the objective function. All right. Okay, so that's what it is. So what I'm going to do is I'm going to save this. Then let me just clear this. So if you go to section 3.1, 3.10 solution, I've actually completed the solution for you. But do not look at the solution until you tried it on your own, okay? The class, I provided the solution for completeness, so that you're not going to come after me to ask me for all the solutions, okay? But basically this is it. So I've done here, and so now the only thing what I've not done is I did not do the chart. When you look at the P here, this is what it is. So now here, if you look at this is the sort of example one. So let me just continue from here. Basically, this is the setup right here. Now, P equals this. Now, P equals this. So how do you actually solve it? When you solve this, P, you write the objective function here. And the first step is usually to eliminate one of the variables. So that finally, the objective function is written in one variable. So we want this function to be written in one variable, and that is using this condition, x, y is equal to 16. If you look at this, what is y? You can either solve for y or x. Y is equal to what? Y is equal to 16 over x. So that's where the 16 over x is coming from. And so replace y by 16 over x. And now the objective function is in one variable. Now what do? We have to take the derivative. So now this guy can now be written in this form using the exponents. So here you don't want to apply quotient rule. Fast. When you apply, if you want to apply quotient rule, always check and see whether you have to apply the quotient rule. All right, whenever you can, avoid the quotient rule. Avoid quotient rule is the worst rule. And many times you cannot avoid. And if you cannot avoid, then I guess you have to apply quotient rule. Okay. All right. So here now we take the derivative, dpdx, and then this. By the way, for optimization here, there are two methods. There are method one. Method one only uses what? Only uses the first derivative. Derivative. Only uses first derivative. Second derivative is not needed. Second derivative not needed. Now let me tell you, there's another method. There's another method, method two. Uses first and second derivatives. Okay, second derivative. However, in this class, I will only teach method one. Those of you who do know how to use the second derivative, okay, use it. But make sure you use it correctly, okay? If you want to use the other method, which is the second derivative, then use it correctly. Because I'm not going to teach you that method. If you're not sure, if it's not correct, then don't use it. In fact, I recommend you not to use it. If you don't know what I'm talking about, then don't use that method, okay? That's what I recommend. Don't use it. Okay, so I'm going to only use the first method, which only uses first. So in this case, example one, so we have what? We have this, we have what? We have dpdx, we have the first derivative, and because this is optimization, we only want to find the max and the min. Second derivative is not required. But in this case, the graphing chart is required. Again, the graphing chart is required. Although graphing chart will be a very simple graphic chart. So what we have is we have x, and we have y, we have p, and then we have p plus dpdx. The second derivative, we don't need. So the chart is going to be simplified because we don't have a second derivative. Also, when it comes to optimization, the charts are usually very, very simple. So in this case, what do we have? We have, what is x? X is going to range from where? X is going to range from 0 plus to infinity. In most cases, nothing happens at the endpoint, so we don't need to know. And then now we look at dpdx, we look at this guy, and so the critical value is 4. Note that negative 4 is out of range. Notice that x equals -4. When x equals -4, yes, the derivative is 0, but this is out of range, out of domain. So we don't need to put -4. We don't need to worry about -4. -4 is out of domain. As you can see, x must be bigger than 0. So now in this case, what is dpdx? The dpdx is what? The dpdx is 0. This guy is 0. When x is bigger than 4, like 5 or something, then what? Plus. This guy is plus. But how about when x is less than 4, or when it crosses over the equivalent value x to 4, this guy's first power here, it changes sign. So now we go down, the perimeter is going down, and the perimeter is going up. Do you have max in here? Max here? Question is, do we have a max? Yes, we do. This is this function is continuous. It's continuous, but x is bigger than 0. Nothing happens when x equals 0, so we don't need to care. So max is 0. Therefore, the conclusion is this. Therefore, conclusion. What is the conclusion? Max p is equal to p when x is equal to 4 and y is equal to 4. I want you to write this down. And what is the maximum? Minimum. Sorry, not maximum. It's minimum perimeter. What am I thinking? Minimum perimeter. And what is the minimum perimeter in this case? Minimum perimeter is going to 2 times 4 plus 4, 2 plus 8 is actually 16. It's actually 16, and then your unit is what? Is it inch? It is actually inch, not inch square, but 16 inches. And by the way, this must be minimum. So let me erase this part right here. It's actually minimum, not maximum. So it should be minimum. That's minimum right there. Okay, any questions here? So this is a structure of an optimization problem. So whenever you have an optimization problem here, you read the problem, and first you do the setup. This is very important. The setup must be done correctly. In this case, the objective function is p. Why p? Because it says find the what perimeter? Find the minimum right there. Here's the keyword. Find the minimum. Minimum what? Minimum this. Minimum. Whatever comes after the word minimum or maximum, that guy is the objective function. Okay? Although the wording might be a little bit different. Find the minimum perimeter. Minimum perimeter. Minimum perimeter. Right there. Minimum perimeter. Or maximize what? Minimum what? So this guy right here is the objective function right here, not the area. We have the area also here, but that's part of the condition. In this case, the objective function is the word or the function which comes after the word minimum or maximum. So with perimeter. So what is the perimeter? It's a rectangle problem here. So the perimeter is 2 times x plus y. And then x is bigger than 0, y is bigger than 0. And the constraint, we have 2 variables here. We need 1 constraint. X squared plus 16 and find the minimum p. Okay, that's the setup. Okay. Any questions on example 1? Now what I like to do now, let me go down here. Let's go down to number.
Excuse me, can you just go back to the red writing so that I can screenshot?
Screenshot? Where's the screen? You know, I don't know whether I can recall the screenshot here.
I think you can do a redo. Yeah, right here.
Oh, there we go. Okay, what about this?
Okay, this is fine. Thank you.
Yeah. Yeah, there we go. I think I already took a screenshot, right? Yeah, I took a screenshot. Yeah. No, that's very matched. Oh, there we go. Now it's fixed. Okay, just to make sure, let me just take the screenshot one more time. Save, and then clear. By the way, when you study, please study with a file which has no solution. Because if you just read the solution without studying and without understanding the problem, then you are literally wasting time, okay? The reason why I did all this is because I usually don't like these answer keys, but I'm under time constraint here. So you are pressured because you have to study. I am pressured because I have no time, okay? So that is my concern. So we both are pressured to study, But again, my worry is that I cannot cover what I need to cover on time, and because my writing is slow. Okay, that's part of the problem here. Okay, so anyway, now let's look at example 2. The solution is already written here. So again, please study the solution after you spend time. Maybe my recommended time is about spending anywhere between 5 to 10 minutes. About 5 minutes, okay? And then if you have no idea what's going on, then you can study the solution. But ultimately, you should be able to what? Do things on your own. You must spend most of the time studying on your own without looking at any solution. Okay, so now let's look at example 2. What is going on here? Example 2, let P be a point on the line x over 6 plus y. Okay, so now let me figure out what this is. Again, if you look at the solution file here, I never drew a diagram. This diagram is kind of hard to draw. And second, I didn't do the graphing chart. The graphing chart is required. Okay? But then this the cell. Okay, so now let's figure out what's going on here. So we have a line, and so the line kind of looks like this. So this is a line. This is a line x over 6, and then plus y over 4. Y over 3 is equal to 1. So now what is the question here? The question is find the maximum area of rectangle. Oh, so it looks like area is our objective function right there. It says maximum area. Area of rectangle lying in the first quadrant with opposite corners 0, 0 and P. At P, what is P? P is a point on this line right here. So that means we have a point P here. And then now rectangle. Now that means we have rectangle like this. Is it rectangle? Is that the red rectangle, or is it the black rectangle like this? Or is it the green rectangle like this? Or is it the blue rectangle like this? We don't know. So out of all the rectangles, what is our job? Our job is to figure out the rectangle with the largest area. We know that when the P is at the end, over here or here, the area becomes 0. So in this case, I'm asking for the maximum because we know that the minimum is 0. Usually in a problem like this, one of them is trivial. Although sometimes you are going to see problems where you have to find the minimum as well as maximum. But most optimization problems, we are interested in finding either min or max, but not both. But again, in some problems, we do want to find the max and the min as well. Okay? So even in business, sometimes there is a min, and sometimes we want to know max and the min. Okay? Okay, so now, why don't we call in this setup here? So what we want to do is, in this go I got to write the important stuff. So let's call this guy P here. Why don't we call this P here, call this guy X, comma Y. I actually told you not to use X and Y and just use A or B. If you're not sure whether you can do this or not, although this time we can, you can call it this P, and then call this guy A, comma B. Okay, all right? Because if you use the letters X and Y, you might get in trouble. And that's exactly what happened on the last test. Last test, you called the slope with something else instead of A. And that was a systematic penalty, a systematic mistake. A mistake you cannot recover. Okay? A mathematical mistake, a systematic mistake, or a logical mistake. That's how I call it. Okay? Those kind of mistakes will blow up the entire problem. They're irrecoverable. You cannot fix it. Okay? So be careful when you use the variable X and Y. So now we call this guy. So now what is it? What's the area? Area is equal to xy. Area is xy, and then x is bigger than 0, y is bigger than 0. Actually, what we can say is that we can say this guy is actually 6, and this guy is 3. You can actually say, if you want, instead of this here, if you want to be a little bit better, if you want to be more precise, you can say this: 0 is less than x is less than actually what? 6. Actually, x is between 0 and 6. And then 0 and then less than y and less than what? Y. Y, 3. If you want to be more precise, you can also write it this way too. Okay? I think that's actually better if you can figure out the answer domain the range becomes the correct range of domain, x and the y. Okay, so we have this. And then, so now this objective function has two variables, two independent variables, x and y. A is just an A. And by the way, the setup will only contain x and y. And the objective function A. All right, and define A, maximum A. So now how do you do this? How do you find it? How do you solve this? A is equal to xy, that's the maximum function. The first step is to express the objective function in one variable. That means from here, from this constraint here, we now get this, we solve for x. Again, you can solve for x or y, but in this case, the reason why I solve for x is because this will avoid fractions. But if you solve for y, then then you'll get into fractions. That's the only difference. Okay, but again, if you want to solve for y and you place the y and write in terms of x, that's okay too. You can write the a in terms of x or y, whichever is easiest. Sometimes the choice of the variable will make a significant difference. Okay, as you will see. So whether you want to eliminate the x and keep the y, or eliminate the y and keep the x, that is something you have to think about. On this problem, it doesn't make that much difference, but on other problems, it will make some significant difference in terms of calculation. And then now, dA, dy, we take the little step to y, and now we get this guy right here. Graph and chart, let's see now what we have here. We have a, and then now we have y, then we have now dy, dA. Or you can write, you can write a prime if you like. If you're a prime, that's okay, but I think it is better to show the independent variable. So dA over dy. The way is, you know what? I wrote it, I made a mistake. What is this? My chart is messed up. My chart is messed up here. It should not be a. What I should have done is, we are so used to writing the y in the bottom here, but in this case, y is actually an independent variable, so we actually put the y here. It's kind of weird. And then here we put the a. So we get this? Yeah. We're so used to putting the y. The y is the independent variable here, not the dependent variable. It's not the function. The function is the area. The independent variable is y, not x, okay? So it kind of looks weird to put the y in there, but that's what it is. And the y ranges from 0 to what? 0 to 3. If you did not know that was a 3, then you might have to just put infinity here. We'll see what the difference is. Actually, nothing happens at these endpoints. When it comes to optimization, what happens at these endpoints? Usually about 90% of the time, nothing happens. Nothing is interesting at the endpoint. So now all we need to do is just 3 over 2. And now 3 over 2 is we get a 0. And then when y is bigger than 3 over 2, so y is bigger than 2, this is plus, and then minus here, and a plus here. That means a is now going up, and then a is now going down. So that means we have what? We do have a maximum here. Is the function continuous? Yeah, the function is continuous. So now the conclusion is, what is the conclusion? Therefore, the conclusion is what? The conclusion is max A is equal to, max A is equal to A, when what? When y is equal to 3 over 2, comma, x equals what? What's x? Y equals 3 over 2, or x equals 3? I want to write this out and write this, what? And what is the area? What is the area? Is xy. Area is xy, and therefore that will be 9 over 2. Okay, let me just write 9 over 2 in fraction form. Yeah, I don't like these slash marks here, so let me just write 9 over 2. Area is 9, x times y. That's 3 over 2 times 3, which is 9 over 2. So I want to write the answers in this format. Tell me what it is, whether it's the maximum or minimum, and then write the objective function, the name of the objective function, and then that's the maximum min, and then of the objective min, and tell me when that occurs. You have to tell me when that occurs, and then tell me what the value is. what is the maximum area? Is this guy right here. But you also have to tell me when that occurs. So this is the way I want you to write the answer. Object function and this is equal to this. Again, is a max or min of the function. Write that down and then tell me the function eval at what point is that the max or min, and tell me what the value is. Anybody has a question here? I want you to give me the answer this way, in this format. Is it already time for a break? I guess so. I guess we have roughly about 45 minutes, and I think in 40 minutes I will be able to go over the rest of the optimization. Yes, the test will be tomorrow. Okay, so let's take a 10-minute break. 10-minute break. A 10-minute break. 10-minute break. Continue at. Let's see, 9:52. So let's look at 10:02. It's 10:03 or 10:03. 10:03:03. Okay. Okay. So let's have a 10-minute break. I'll be back in 10 minutes.